Alright, today let's talk about section 6.3 in your book, volumes by cylindrical shells. So last time we talked about how to compute volumes using the disk method or washer method, and sometimes that's not the best way to compute a volume, so here's just another way to do it. Yeah, this is just your chapter in your book. I'm just gonna go through it and read through it basically. Okay, so skip all this nonsense. Let's start with an example of this, cylindrical shell. You can see we take a larger cylinder of radius R2, then we have this smaller cylinder of radius R1 that we remove from it. And we want to figure out what's the volume of this thing. Well, the volume for this thing should just be the volume of the larger cylinder, one with radius R2, minus the volume of the smaller cylinder with radius R1. We talked last time the volume of such a cylinder is pi r squared h, where r is the radius of the cylinder. So when you subtract off those two volumes, you get this formula for it. And now, for reasons that will make sense later, we're going to rewrite this expression for the volume in a certain way. So we have this difference of squares, so we can factor it out as like this: R2 plus R1, R2 minus R1. And then we'll go ahead and multiply and divide by 2 here, so that way the volume of this cylindrical shell that we're computing can be written as 2 pi times this quantity here, which is the average of the two radii, times the height of the cylinder, and then R2 minus R1 is the difference in the two radii. So if we call that the average of the two radii r and the difference of the two delta r, then what we just showed is that the volume of the cylinder is 2 pi r h delta r. I'll write it down here. The volume of this cylindrical shell with this kind of setup is 2 pi r, average radius, h, height, delta r, difference of the radii. So there's that formula there. And now reason why we rewrote the volume in this way is because it gives us an easy way to remember it. This 2 pi r is the circumference of this cylindrical shell. So if you look at this average radius here, this middle point, and you look at the circle that it makes going around, and you ask yourself what's the circumference of that circle, it's 2 pi r. So we have circumference, how much around, and then height, how tall it is, and then thickness, delta r, is how thick it is. So that's an easy way to remember the volume of this cylindrical shell here. Okay, so that's what that is. Now, how do we use this to compute volumes by the cylindrical shell method? So let's take a look at this example here, where I have, say, between some points A and B, I have a curve given by y equals f of x, and we look at the area that the curve makes between this and the x-axis. And then we rotate this around the y-axis, so it makes this 3D looking shape here. Okay, this volume of revolution. Okay, and what we want to do is we want to compute the volume of this thing. So skip all this. I guess I won't skip all the nonsense here. So what we did in the previous section was we, wherever the axis of rotation was happening, we would cut this area perpendicular. So in this case, we'd cut things in the, we'd cut this area in the along the x direction, and divide it up into small horizontal pieces. And when you rotate that around, rotate each of those small pieces around, that creates a disc, well, a washer, and then we'd have to compute the washer. Now what we're going to do instead is, instead of chopping things perpendicular to the axis of rotation, we're going to chop things up parallel to the axis of rotation. Okay, and we chop things up. Wow, this picture quality is bad, but oh well, that's what your book gave. So let me zoom in a little bit. Oh, wow, that's bad. Whatever. When we chop things up horizontally into these thin little strips here, and we rotate that around, that creates this thin cylindrical shell, that thing that we just figured out what the volume was of it. And so when you do that for all the pieces here, all these little cross sections, you can see that it creates this whole family of nested cylindrical shells that, if you stack them on top of each other, it looks pretty close to the actual 3D shape that you're trying to approximate. And so if we compute the volume of these stacked up cylindrical shells, that should give us a good approximation to the actual volume we're trying to compute. And as we make our cylindrical shells thinner and thinner, and we take more and more of them, we get a better and better approximation. So how do we compute the volume of this stacked up set of cylindrical shells here? Well, we just use what we just did. We know how to compute the volume of one of them. Say if I'm at a point, this is supposed to be read xi, and I create a, I make that my center point, and I create a shell with a certain thickness. Call it delta x, xi minus xi minus 1, and I rotate that around, and I call this volume vi. To compute that volume vi, it's just circumference times height times thickness. Well, the circumference is just 2 pi times the radius of this thing. The radius of this thing comes out to the point xi bar right here, so there's circumference. The height of this thing goes from y equals 0 to y equals f of xi, this fxi bar term here. So the height of this cylinder is just that. And then the thickness of it is xi minus 1, which we just call delta x. So that gives us the volume for just one of these things. Now if I go to a different point, compute that volume, a different xi, the formula is still the same, it's just that the particular values xi changes. And so we compute the volume of the next one, we add to it. So the point is, if I want to approximate that volume, it's given by this formula here, where you add this sum 1 to n is however many of these you have, however many of these shells you have, and we just compute the volume of each shell and we add them all up. Okay. And like I said, as we take more and more shells, this approximation gets better and better. So that means we let n get larger here, and this delta x, because delta x is the difference between two of these points, gets smaller. The point is, as we let the number of shells that we take go to infinity, we take this limit, we get that the volume becomes exactly this thing. But if you look at this limit, you just remember what the definition of an integral is. the limit of the integral, you just have this function here. You're taking its value, its height, the height of this function, the value of this function at different points, and you have the difference between points. You let that thing go to infinity. This, by definition, is the integral of this. The integral of this function here, 2 pi x f of x. Okay? So, to summarize everything I just did, all this is to say that if you have some curve, y equals f of x, going from a to b, and you rotate that curve about the y-axis, and you want to find the volume of the resulting shape, it's just you get the volume of the really tiny cylindrical shell at the value x. You get that volume, and then you quote unquote add up all the volumes. You integrate the volumes. 2 pi x f of x dx. That's how we compute it. Okay. Yep. Circumference, height, thickness. Integrate. That's all that's needed there. So let's see. Now let's see how we use this and look at examples. So we'll take the particular curve y equals 2x squared minus x cubed, and we'll look at that. So that's what the curve looks like this if you were to solve for where the x values where y equals 0, you get x equals 0, x equals 2. Yeah. And we want to integrate the area between this curve and the x-axis. We want to rotate that around the y-axis. We want to find the volume. And it's doing things with the shell method is as simple as for a particular x value, you draw the cylindrical shell that comes from it. You figure out the radius of that shell, so it gives you the circumference. You figure out the height of that shell, and then the thickness, because this is along the x direction, the thickness is just dx. So yeah, when we do things like this radius here is just the distance from the axis you're rotating to the point that you're at, so that's a distance of x. The height of this thing at x is just, well, here's the curve y equals f of x, so the height is just f of x, 2x squared minus x cubed. And then the thickness, dx. You get the volume of one of these really thin shells, and then you have to add up all the volumes, which that means you integrate from x equals 0 to x equals 2, because that's what gives you all the volumes of all the little shells. Yeah, so when you do things like that, yeah, the integral, just to set up, it becomes this. So 2 pi x, that's the circumference, height, 2x squared minus x cubed, thickness, dx. And now you've set up the integral. It's just a bunch of polynomial terms. We can integrate that stuff. Here's the details here. Gonna go back, read on your own, work it through on your own, but the final answer you get is this number here. Who cares? The important idea is getting this set up right here. It's getting this set up here. The only thing you have to remember for shell method is circumference, height, thickness. Circumference, height, thickness. Alright, pretty simple. But let's look at even more examples, so that we can so we can see some more things in practice. Okay, so now let's see what happens, how we apply this idea of circumference, height, thickness, all that stuff whenever the function whenever we're looking at an area bounded by two different curves instead of just one curve and the x-axis. So I have the function y equals x and y equals x squared. If I look at the region bounded by those two curves, here's the line y equals x, here's the line y equals x squared. They intersect at the point 0, and that's the point 1 there. You can solve for it. Set x equals x squared, solve for the points, that's x equals 1. And now, when I want to do the shell method, I'm rotating about the y-axis, so I still cut things parallel to the axis I'm rotating about. So when I'm at a point x and I cut vertically there, the only thing that changes is I just have to be a little bit more careful about how I compute the height. So in this example, to compute the height of this cross section here, it's just the top curve minus the bottom curve. That's all it is. Yeah, so if the top curve when you're at x is y equals x, so that value here is x, and this value down here is x minus x squared. So when you, sorry, the value down here is x squared, so that the shell height is the difference between the two, x minus x squared. The radius of this thing is still distance from the axis you rotate to the x value that you're at, so that distance is still just x. And so the volume of one particular shell is still circumference, height, thickness. 2 pi radius, 2 pi x, height, x minus x squared, dx. We're integrating along the x-axis, so the thickness is in the x direction, dx. Okay, so that gives us the volume of one of the shells, but now we want the volume we obtain the full volume by adding up all the shells. Okay, and so we get that by integrating. We integrate from x equals 0 to x equals 1. So that's how we get this here. That's how you compute the volume using the shell method. Just 2 pi x, x minus x squared, dx. And then you can do the rest of the computation yourself. You get this number pi over 6. Who cares at the moment? The important idea is this first step here, setting this up. Okay, that's all that is. So let's just compare this with the last example. The last example, we had just one curve and then the x-axis. Well, you can think of this as a special case of the other example. It's just you have y equals 2x squared minus x cubed and y equals 0. So the height is still just the distance top curve minus bottom curve. It's just our bottom curve, and this example was a special case. It just happened to be one of the axes. But yeah, you should always think of height as top curve minus bottom curve. Top curve minus bottom curve. Okay. So yeah, same here. Top curve minus bottom curve. Top curve minus bottom curve. So you really are just doing the same thing. You just have a slightly different example. Yeah. Okay. So that's all for that one. Now we talked about rotating about the y-axis. We can also rotate about the x-axis, just like we did with the washer method. And the basic ideas are still the same. It's just everything's turned on its head. You're making shells that are rotated and going in another direction. But the basic principle is still going to be the same: radius, height, thickness of a shell. So let's look at the example here. So we have the curve y equals square root of x, and we look at the area under this curve. So y equals square root of x and y equals 0. We look at the curve, the area bounded from that, and you go from x equals 0 to x equals 1. So the picture looks like this. You have curve y equals square root of x. X goes from 0 to 1. You have this area here, and now we rotate it about the x-axis instead. So we rotate this way. And the setup is still the same. It's just essentially X and Y get their roles reversed in this from the previous examples. Yeah, so to set up the shell method, the cross section you have to do parallel to the axis you're rotating. So if we're rotating the X direction, our cross section is going to be in the X direction. Okay. And so when we set up a cross section like this at an arbitrary height Y, if we were to rotate, I guess it doesn't give us a picture this time, but if we were to rotate that around, that would create a cylindrical shell going out of the page and down and back into the page and back up. But we can still compute the volume of that thing. Doesn't matter if it's rotated on its side or if it's facing straight up like how it was before. It's still just circumference, thickness, and height. So what's the circumference of this thing now? It's still 2 pi times the radius. It's just the radius now goes in the y direction instead of in the x direction like it did before. So radius is still just distance from the axis to the value that you're at. So in this case, the radius is y. Okay. And now we need the height of this thing. Well, the height is still quote-unquote top curve minus bottom curve. It's just since we're going in the x direction, that's the positive x direction. It's probably better to think of the positive curve, the more positive curve minus the less positive curve, because then that doesn't matter whether you're thinking left to right or top to bottom, as in the previous case. The more positive curve minus the less positive curve. This x value, these x values here are more positive than these x values. So that's why we do right curve minus left curve whenever you're doing things in the x direction. So anyway, the height of this thing, here's the value x equals 1. Okay, x equals 1. And now the value here, I need to subtract off the x value here on this curve. Well, the only thing I know is that this point here lies on the curve y equals square root of x, right? So if you were to instead solve for that, solve this for x, you'd get x is y squared. So at height y, this corresponding x value in this curve is x equals y squared. So you have the x equals 1, x equals y squared. You subtract off that distance. The height is 1 minus y squared. So that's the shell height, 1 minus y squared. Okay. And then the thickness, since the thickness, the shell's got thickness in the y direction now, the thickness is just dy. And so the volume of one particular shell, it's still the same, circumference, height, thickness. It's just everything's in terms of y now instead of in terms of x. Okay? So yeah, circumference 2 pi y, height 1 minus x squared, thickness dy, integrate y. These y values go from 0 to 1. How did I know it goes from 0 to 1? Well, the area here goes, in the x direction, goes from 0 to 1. We were told that. And this is y equals square root of x. So when x equals 1, this y value is square root of 1, which is just 1. And so to add up all the volumes from all the shells, y has to go from 0 to 1. So, yep, same fun little setup here. This is a pretty easy integral to compute. You just do it. I'll let you work those details out on your own, and you end up with the value of pi over 2. Okay, whatever. Cool. Just the important thing every single time is how do I set this up? And yeah, circumference, height, thickness. Circumference, height, thickness. Okay. Now let's look at this example where, yeah, so all the previous examples I was rotating about one of the axes. let's look at an example now where we rotate about a different line. We'll see that if you just stick to the basic principles of circumference, height, thickness, and you just understand what circumference means, it doesn't matter what line you rotate about. You can still use this method and it works out well. Let's just figure out how to set it up. Okay, so I have the curve y equals x minus x squared, and I look at the area under that curve between that and the x-axis. So this is x equals 0, this value is x equals 1. You can solve for that root, just set that to 0, solve for x, you can find x equals 1. And now I rotate this not about the y-axis, I rotate this about the line x equals 2. So if that's x equals 1, x equals 2 is out here. So you see the picture, here's where the original area is. When I rotate that stuff around, it creates this symmetric looking picture. Not symmetric about the axis, but symmetric about the line x equals 2. Okay, whatever. We can still handle this. So I want to know the volume of the resulting, when you rotate that resulting shape. It'll kind of look like looks like a bagel if you cut the bagel in half. Long ways before you cut the bagel in half when you're putting cream cheese on a bagel or whatever. So yeah, they give you a picture. So anyway, how do we do this? So my axis of rotation is vertical. So I create my cross section parallel to the axis, which means my cross sections are also vertical. I'm at an arbitrary x value, so I cut things up vertically. I'm at an arbitrary x value between 0 and 1. When you rotate that small cylindrical shell around, it creates something like this, okay? Where the value here is to x, and this is the center of the shell. So the radius is the distance from this line x equals 2 all the way to that point x that you're doing here. Okay, it's that positive distance right there. Okay? And now if I want to figure out the circumference of this thing, I need the radius of this thing, so I need this stuff in between here. I need that stuff in between there. So how do I do that? Well, the distance from 0 all the way out to x equals 2, this whole thing is 2, and that small part is x. If you call that thing r, you set up the equation r plus x equals 2. Solve for r, you get this radius is 2 minus x. Okay? That's the radius, 2 minus x. Alright. And now the height of this thing is just top curve minus bottom curve, or more positive curve minus more negative curve. In this case, the y value here is x minus x squared, and the y value here is x is 0. So it's just, that's the height, x minus x squared. So that's the height of this thing. The radius is 2 minus x, and the thickness, since we're going, since we're creating our shells along the x direction, the thickness is dx. So you put it all together, circumference, height, thickness. The circumference is 2 pi radius. The radius just has a slightly different formula now. Just always think of radius as distance, so this should always be a positive number. Distance is positive. Distance from the axis you rotate to the point that you created your shell slice at. Distance from axis you rotate to point you created your shell slice at. That's this radius. Okay? And if you just draw a picture, you can always compute, you can always figure out what that distance is supposed to be. So 2 pi radius, height, integrate the x goes from 0 to 1 in order to get all of the shells you just created. And now you just integrate this polynomial. Not bad. There's the volume. Okay, cool. Important thing was how to set this up. So yeah, pretty straightforward. Let's see, what's next? And that's it.